Here we are with 6.4, which is sampling distributions and estimators. So the main objectives of this section is understand the concepts of sampling distributions of a statistic. Basically, which is the distribution of all values of the statistics when all possible samples of the same size are taken from the same population. In other words, what you're going to do is you're going to take a bunch of samples and then actually make a sampling statistic, or having a sampling distribution about all those basically samples you took. So basically running a bunch of trials. And you'll see here in the next slides that might make that a little more definitively clear. Basically, sampling distribution of statistics can be something from like a sample mean or a sample proportion. We can also do the sampling distribution for variance and sampling distribution of a proportion. So normally in class, I'd have us do this one. Basically, sampling distribution of the means, considering repeating this process. Roll a die 5 times and find the mean of X bar of the results. What do you know what the behavior of all the sample means that are generated as this process continues indefinitely? So bottom line, if you did this roll 5 times, but then you did it like 100 times, you'd have a sample mean from each of those times. And that's going to make your sampling distribution. So some notes to happen out of that example that hopefully we would see is that the sample means target the value of the population mean. That is basically the mean of the sample means is the population mean. The expected value of the sample mean is equal to the population mean. The further out we draw this, the more accurate it shows that. The distribution of the sample means tends to be a normal distribution. This will be discussed further, right? So this is, I think, maybe a better visualization. If you imagine, basically, these are the first sample. The first time you roll the 5 die. The second time you roll 5 die. The third time you roll 5 die. And this is in 10,000 trials. So you might think, holy crap, that's a lot of trials. Well, this is where you use computer software to generate these kind of metrics for you. In this case, what do you notice about the histogram? It looks approximately normal with the sample mean right about 3.5. In fact, from our data, we have 3.49. We expect from the population for it to be 3.5. And again, we can do this for all of the values we are looking to test. So like means, variances, and proportions. It's pretty neat. One thing you'll notice though is variances are skewed and proportions are approximately normal as well as following means. So the variance, the sample variance targets the value of the population variance. The distribution of the sample variance tends to be a distribution skewed to the right? Remember that means positively skewed. So unbiased and a biased estimator. An estimator is a statistic used to infer estimates the value of the population parameter. So that's basically what we're doing by doing all these trials, right? An unbiased estimator is a statistic that targets the value of the population parameter in the sense that a sampling distribution of the statistic has the mean that's equal to the mean of the corresponding parameter. So what it means is that basically if you repeat these trials, the sampling distribution you get should target the population parameter's value if it's an unbiased estimator. So there are some of the unbiased estimators, mean, variance, proportion, and then some of the biased estimators, the median, the range, the standard deviation. So why sample with replacement? All the examples in this section involve sampling with replacement. 2 reasons why we're interested in sampling with replacement. Basically, when you're doing a small sample from a large population, it makes no significant difference whether we sample with a replacement or without replacement. In other words, you're kind of assuming everything is independent in that case. Sampling with replacement results in independent events that are unaffected by previous outcomes. And as you know from previous calculations, it's easier to calculate independent events than it is dependent. And that is all 6.4. It's really quick, short. Let me know if you have questions.